Hey, calculus students, and welcome to this extra example video on computing solids, volumes of solids by slicing. Today we're going to look at a couple solids that are not solids of revolution. There's no reason we can't do those as well. But of course, and we did one in class, but not a lot of time for these in class. It's just the way it goes, but we'll get you a couple more examples of these on this video. Okay, again, our method's going to be slicing as always, so we need to be able to find areas of those cross sections and go from there. So let's take a look at our first example, and this example comes from Hoffman's book, and that is again a free online calculus textbook linked on Canvas, and it's a great resource for extra problems and a little bit different perspective, so I highly recommend it. Let's see, what color did I leave myself here? Yeah, red. Okay, we'll go with red. I'll put myself over here. Okay. So here we are given a solid that's, you kind of got to use your imagination to see where it is a little bit. We got an x and a y axis here, not put in real clearly, but the y axis is right there, and x axis you can see. So the solid, it's presumed here, it starts at the origin, if you want to think of it that way. It goes out till 3 here, and what's shown is kind of the last cross section. Then we got 2 cross sections shown in the middle there. So let me first mention that the solid extends from x equals 0 to x equals 3. And from that we already know what our limits of integration are going to be. Then we look at the cross sections. The cross sections, I think you could see, are triangles. They're right triangles, in fact. And that's great because we know how to find the areas of right triangles, at least as long as we know the base and the height of those triangles, which we do. So if you think about slicing at a particular x here, like some x value right there, the important thing is going to be to find the height of the triangle. Okay, so we need this right here as our height, and you can see that that's going to be the y coordinate. That's supposed to be a y. It's going to be the y coordinate of that point. Now, the line that we have there is y equals 2x. So it's going to be easy. If we're at x, our height is going to be 2y. And then conveniently here, we also have that the base of our triangle is 1/2 of the height. So when looking at the areas here, so for the area of a cross section, we've got a of x. So those cross sections are going to be varying with x. A of x is going to be 1/2 base times height. And at x again, our base, well, our height is going to be 2x. And our height is going to be x. So when this all shakes down, it turns out that the area of the cross section is just x squared, which is great because now we can do the volume of one of our slabs here. And as long as we use a slab of differential thickness, as we tend to like to do, our volume is going to be, our differential volume is going to be a of x dx. And so that means it is just x squared dx. And so this now we just have to add up those differentials of volumes, and the computation becomes pretty easy at this point. It's going to be the integral from 0 to 3 because that's where our solid extends along that x-axis. And our differential volume is x squared dx. Okay, and so we anti-differentiate using the fundamental theorem of calculus here, x cubed over 3, evaluated at 0 and 3. And so we get 3 cubed over 3 minus 0, and that turns out to just be 3 squared, which is 9. Okay, so this solid has volume 9. And we'll leave it to you to check whether that is a do an estimate maybe on that to make sure it's reasonable. And I'm hoping that you'll find it is, but we won't dwell on that here. Let's go to an example that's going to be a little more involved. Okay, so here we want to derive the formula for the volume of a pyramid. And the pyramid has height h, and the base of it's a square, so it's your typical pyramid. And the volume of that, and it's a known formula, volume is 1/3 b squared h. But now, how do we know that that formula is true? Well, we can verify it with calculus. Certainly not how it was done originally back in the ancient world, but we can use calculus for it now. So the first thing we need to do, since this situation does not come with a coordinate system, prefabricated, we need to make one. And what I'm going to do this time, okay, you may question my judgment here, but I'm going to put the y-axis right down kind of the axis of the pyramid here, and then I'm going to put the x-axis like so. So my axes here are within the plane. If you think of vertically slicing this pyramid kind of right down its center so that your cross section is the largest possible triangle, that is where our axes are located, in that plane. And I'm going to put 0 on the bottom. I kind of have a feeling that it might make certain aspects of the computation a little easier if we put 0 at the apex of the pyramid and then had our y-axis pointing down. You might want to try that and see how it compares. But I think the natural thing that people are going to tend to do is to put 0 at the bottom and probably at the very center of the base of this pyramid. And so let's do that and just show that even though there may be a little bit of complications that arise, we can still deal with those complications just fine. So I'm going to note that h is y equals h is where the apex of that pyramid is going to be. Okay, so now if we want to make our cross sections as simple as possible, especially with these coordinates we've set up, we're going to want to slice perpendicular to the y-axis. And in doing that, our cross sections are all going to be squares. We know finding the areas of squares is pretty easy. And I think I'd like to get yet another color here to help keep everything distinguished. Now it's getting close to it. Let's go with bluish. Okay, so let's say we're at a particular height y, which we'll say is right there. And then that cross section that we're going to get is going to be like this. Again, maybe a little hard to tell from the angle we're viewing this at, but that's going to be a square, right? Let's take it, turn it sideways so we can see it a little better. Okay. So there's our cross section, and if you take a look at what the side length of that's going to be, the x coordinate that we're at the kind of right hand edge of our square, that is going to be half the side length. Okay, so x is half of this here, which means the entire side length is going to be 2x. And since it's a square, the other side will be 2x as well. So far what we know is that a of y is going to be side length squared. So that's going to be 2x squared, which is just 4x squared if we square the factors separately there. That's all well and good, but we need this in terms of y. Because we are slicing perpendicular to the y-axis, we're going to want to integrate with respect to y, so we got to figure out what that x is in terms of y. Now, there's two approaches you can take to this. We can either use analytic geometry, get equations for the lines involved and things like that, or we can use triangle geometry, synthetic geometry it'd be called, and I think I'm going to go with synthetic geometry. Okay, so let's make a triangle in here that is again in this plane that cuts through the apex of this vertical plane, cuts through the apex of our pyramid. And let's take a look at that triangle right there. Okay, so you see that the hypotenuse of that triangle lies on a line that we could find the equation of. In fact, this x-coordinate right here is going to be b over 2 because the whole side length is b. And with the symmetry here, we've got half of that to the right of our origin. Okay, so the triangle approach here, if we use that, okay, we've got this triangle right here, and that again, half of the largest triangle cross section that's vertical. Okay, and now for the particular y that we're at, we get a smaller triangle above that. So this length here is y. We know that the length all the way to the top of the pyramid is h. And that means that the side length of this small upper triangle here is going to be h minus y. Okay. Oh, and now what about our bases of these two triangles? Well, we know that this one is b over 2, and the upper one is x, and that is actually what we're trying to find. We need to replace this x in our formula here with something in terms of y. So using the proportionality of sides of triangles, of similar triangles, we can relate the side lengths here. And looking at the smaller triangle, we could do, base over height of that is going to be x over h minus y. And set that equal to base over height of the larger triangle. So that'll be b over 2. Let's see, b over 2, yeah. b over 2 over the height of that larger triangle, which is going to be h. Pause this for a second here. Again. That's our dog Ginger, as you could probably tell. Okay, so we had the ratio of our side lengths set up, this proportion here. And what we want is to get x, so we can do that just by multiplying over. X now will equal, let's see, if we kind of simplify this complex fraction, we get b over 2h. Oh, important here to distinguish clearly between b's and h's. And then we've got h minus y. And we could distribute the b over 2h. I don't think that's really gonna help anything too much, so I'm just gonna leave it as is. Okay, so back up to the area of our cross sections now. We see that that's going to be 4 times, well, we're squaring our x values, so we're going to, if we square the individual factors, we'll get b squared, that one's a b, over 4h squared, and then h minus y squared. I don't think there's going to be a lot of benefit in foiling that out, so we'll leave that as is. But one nice thing that we can do is cancel those 4's. So it's going to be b squared over h squared, h minus y squared. Okay. All right, so that's the area of one of our cross sections. We know that to get the volume of a slab there, we just thicken that up with a differential factor of dy. And then we integrate across where our pyramid's located. So the pyramid starts at y equals 0, and it goes up until y equals h. So that means that our volume here is going to be the integral from 0 to h of our differential volume. So that's b squared over h squared, h minus y squared dy. Okay. Now we know that the b squared and the h squared can pull out. Maybe we'll do that as a preliminary step here. B squared over h squared, integral from 0 to h, because the variable of integration here is y, right? So everything else, even though we got letters representing those things, their parameters, we consider them as constants here. The real variable, the actual variable here is y. That is what is changing. Okay. All right, so now we do need to do a trivial substitution on this. It's trivial because, I mean, the inside function there, h minus y, is linear in y. But do remember that when we do that trivial substitution, we need to divide by the linear coefficient. Linear coefficient here is -1, so we got to get that in there. So we're going to have h minus y cubed over 3. But then we got to divide by -1, so I'm going to throw a minus sign in there as well for that. Okay, and again, you can review the rationale for that in the review of integration from Calc 1 posted on Canvas. Okay, so now let's evaluate at our limits of integration, putting h in there. So, okay, we got the b squared over h squared out front. Putting h in, we're going to get h minus h. So that'll just be 0 cubed over -3. That term is going to go away, and then we subtract what we get when we plug 0 in. In this case, that is going to be the interesting term. So we will get h minus 0, which is still just h, over -3. Oh, but this is cubed. Okay, and that's that. But let's simplify it now. Again, first term 0. The minus signs will cancel here, leaving us with h cubed over 3. And so we get b squared over h cubed over h squared, let's say, times h cubed over 3, which we can cancel a couple factors of h there, and we end up with 1/3 b squared, one factor of h left in the numerator, 1/3 b squared h. So at the end of the day, the formula we get for the volume of that pyramid is v equals 1/3 b squared h, just as we've always been told it is. And now we have confirmed, verified, derived that formula using calculus. Again, not a solid revolution, but as long as we have those cross sections that we can understand and work up a formula for the area of, it's still all just as good as with the solids revolution. All right. Hope you enjoyed this extra example video, and we'll see you again soon.